Look at the future, and that's the purpose of our panel. We have a technology panel today and a business-oriented panel tomorrow. I'd like to invite the panelists to take their seats. And while this is happening, just a note. Today is June 5th, and many Israelis are looking backwards to the past, 50 years to the past. Incidentally, and that's an opportunity to also think about the future. Same about technology. Danny Lubzins just told me this morning that CMOS patent was awarded in 1967. So 50 years ago, we got CMOS, and we stayed with CMOS until now. And many people today said that the future will look totally different. And at least one, where is Stan? Where is Professor Stan? Said that Moore's law is not dead. But we heard terms like spintronics and flatronics and STT MRAM and resistive RAM and Memristors and CNTs and ribbons. So all of these technologies are candidates to replace CMOS. The question to the panel is about the future. And before we start, I would like the panelists to introduce themselves briefly within about 30 seconds each. Go ahead, please. Microphones.
Good afternoon. I'm Michael Kozicki from Arizona State University. I guess I was about to say claim to fame, but I'll say my curse is being involved in the RRAM field for over 20 years now, and successfully helped to drive an RRAM technology called CBRAM to commercialization. And looking back, they say it's dangerous to try and drive a car by looking in the rear view mirror constantly, but I certainly learned a lot of lessons that hopefully will help guide us for the future.
Yes. I'm Eli Yablonovich from Berkeley, and I'm the director of the NSF Center for Energy Efficiency and Electronics. And so I already spoke, and you've heard some part of that, so let me look forward to the questions during the panel discussion.
Okay. My name is Thomas Mikolajczyk. I'm the scientific director of NAM Lab in Dresden, Germany, and also a professor for nanoelectronic materials at TU Dresden. And some of you have also been in my talk already, so let's look for the discussion.
Thank you. I'm Jakob Roizin. I represent Israeli foundry Tower Jazz that has fabs both in Israel, in the United States, and in Japan. I hold the position of Tower Jazz Fellow, and I'm directing activities related to emerging technologies. And I'm also a little bit teaching. I'm a visiting professor in Technion and in the Tel Aviv University. Thank you.
Hello, I am Amir Regev. I'm the VP R&D of Weebit Nano, an Israeli startup company that is working to commercialize RRAM technology. And I don't know if you noticed, but I'm the only one in this panel that is not a professor. So I can bring my experience of 20 years in the semiconductor industry in the University of Life.
Okay, so I encourage everybody in the audience to participate with questions and opinions. And just for starters, I'd like to address the panel and ask, among all of these technologies that we heard about today, who are the winners and who are the losers? I think Professor Yablonovich wanted to be the first, so please go ahead.
I'm not sure I want to be the first, but I do have an answer to that question. I was, like yourself, very impressed by Mircea's presentation from the University of Virginia, where he pointed out that by building the FinFETs taller and taller, you get more conductance. Conductance was one of the 3 requirements that I described, and more conductance means more speed. So I think we can expect, surprisingly, further progress along the speed axis. So I'm very encouraged by that. But unfortunately, it says the future does look more like the present because it's more silicon. But in the terms of speed, I think we can expect that.
So who are the winners and who are the losers among all of the myriad of names we heard today?
Well, that was one winner. I'll let other people select other winners.
I had to give do an IDM panel once, and we all agreed at that for the next panel, and we were all talking about our respective technologies, for the next panel we had to bring along our talks stored on the memory devices that we were actually talking about. So I think if we can claim that, then that's a reasonable win, I think. In other words, is it commercially available? I think that's I guess it was Stefan Lai said that for any new technology to get anywhere, it has to have a beachhead. It has to have a little finger in the market to kind of help pull itself up. And I'm happy to say that RRAM certainly is moving forward in that respect. I mean, it may be kind of niche at the moment, but it's certainly it's kind of moving.
So if you would like to replace CMOS, you would have to jumpstart into a development that has been going for 50 years now. Because to be competitive, cost-wise, you would have to reach the same complexities from day one. I don't think that can be possible from a technical or scientific point of view. So that's why I foresee that we see several of these technologies that we're discussing today as add-ons to CMOS rather than displacing them. But you asked for winners. I don't like to talk about losers because I don't know. We have to try more than one, yeah, definitely, and we have to bet on several choices because the future is always hard to predict. But one winner I see, what I really think is disruptive, is what we saw from the NAND flash, going towards the third dimension, this punch and plug technology. Because if I talk to my students and I explain the memory technologies, I always compare a hard disk drive to a semiconductor memory. And I tell them, guys, in a hard disk drive, you only have one access unit to access all the bits. So if you go to very high densities, you can never beat it with a semiconductor memory. But now comes 3D NAND, and the situation has changed because we do punch and plug. And Hynix has announced they do 72 layers on top of each other with one critical litho step. So this is really disruptive, and I think we have to think how can we apply such ideas also to other technologies and more general architectures than just doing strings of NAND memory.
So the winner is?
So,
vertical flash?
No, doing 3D integration in a manner where you don't need critical lithos for every layer. So, for instance, Stuart's racetrack is going into the same direction. He showed that he has to have one racetrack with lots of bits and only one writing and one reading unit. So I think that's the direction to go, at least for very high density circuits and very high density memories.
Okay.
Thank you. I think that there will be several winners. We will see winners according to applications. That's why the answer to this question is actually first to specify the application and then to say the winner. In the field of substituting standard CMOS for means of computing, I don't see any candidate that can compete today with what was achieved with scaling of standard CMOS. Maybe the most close solution, and I agree with Thomas, so actually it's a kind of a integrated magnetic memory that actually acts both as SRAM and non-volatile memory. It could be, for example, racetrack memory, which was excellently explained by Professor Stewart, and it's actually one of the enlightening solutions, I guess. Among other solutions from the same field, I speak about it not because we are the only foundry that have in production magnetic stuff integrated into CMOS. It's a true actually comment. Another probably spin orbit transfer memory, spin orbit transfer cells. All the memories which were considered as universal memories do not work due to reliability limitations. All that use magnetic tunnel junctions suffer from reliability limitations connected with forcing large currents through magnetic tunnel junctions. And so one of the candidates, as we already discussed here, is the racetrack memory, which due to the, I think it's a breakthrough achievement related to AFM that can decrease currents in these memories. This is one of the candidates for future use together with CMOS on the CMOS wafers, and the other is spin orbit transfer probably. But once again, it's not a kind, I don't want to be a prophet, it's impossible to be a prophet in our science, and I want to repeat once again, it depends upon the application, upon the applications. For example, in applications that connected to Internet of Things, low power consuming, there are several candidates. Thank you.
Yeah, I would like to add that the market is changing. The requirements are changing all the time. So it's not the game is not over. And it is a little bit difficult to predict what will be in the future. Like 10 years ago, everybody's talking about flash replacement and just storage. And now we're mixing between memory and storage. And now we're getting into using memristors, talking about using memristors within the logic, and I try to learn new stuff every day, and the first thing I learned today was in Unu's presentation in the morning that I'm not the only one, I'm not the only scientist here that has a BA in psychology. So it turns out now that trying to understand how our brain works, and if you looking at it at this perspective, and you start seeing the application of artificial intelligence is getting into our daily life without even us being noticed about it. Like every time you're doing a Google search and they suggest you which movie to look at, and everything is artificial intelligence and street view, and everything is getting into our daily life now, trying to mimic how the brain works and trying to do that using how to do that in hardware and not just in software, and getting the energy efficiency, the parallelism, and the performance of the brain is something that I think will start getting to get a big traction in the future.
Okay. Neuromorphic session is tomorrow.
Okay.
Okay.
But we people.
Yeah. Also, that's where I want to agree with you and give an example. So we had this morning one of the speakers, and I apologize, I've forgotten your name, who was talking about various types of analog machines to do this type of, not just associative memory, but all sorts of very interesting things, including matrix vector multiplication. Yes, introduce yourself. Yeah, so that was terrific. Thank you very much. And let me sort of describe the way I envision it. If we go back to 60 years, that was the middle of the 1950s. I was a very young child, and I was told, the guy was interested already in science, I read various magazines, and I was told that there's a competition between the analog computer and the digital computer, and that no one knew which one would win, okay? Of course, we know now that the analog computer was a joke, and the digital computer won. However, we need to go back and re-examine why the analog computer failed. And that was because we were putting in analog accuracy, and the answer was also analog accuracy, so we never got enough precision to be useful for anything. But the situation has changed a little bit. And the change is that we were thinking the wrong way about analog computing. We should have had digital inputs into the analog computer and digital outputs from the analog computer, then everything would have worked out. Now, there are concepts now that we heard about this morning is, for example, the icing machine. We can make an analog icing machine. Now, an icing machine has been proven to map onto NP-complete hard problems. That is to say, very, very hard problems. We can solve them with some degree of precision using an analog machine. And as long as we expect only a digital output and a digital input, the analog inaccuracy doesn't matter. And so we have a number of great examples that the professor from the University of Rochester told us, that where we don't need fantastic accuracy and we can still get tremendous speed-ups for answering things having to do with deep learning. So I think you were referring to deep learning. Deep learning is a revolutionary development for the future because deep learning is, as you said, you do a language translation, language recognition, photograph identification. All of these things can be accelerated tremendously, perhaps by using these analog accelerators, which have digital input and digital output.
Yeah, so this brings me to my second question before I open it up for the audience. You people talk about applications. So my question is, what is the killer application that will create innovation? Is it to have agreement? Do we have agreement that this is deep learning? Or is there another killer application? What do you think? Anybody in the audience?
Okay, you have to come up with something better than deep learning.
I'm not so sure if we will see in the near future, again, one of these one application that everybody is striving at. I think it will become more diverse. So we see a lot of decentralized smaller applications, and the big challenge will be how can we create platform technologies and make use of this wonderful semiconductor technology and still create a mass market, although the applications will be much more diverse than we were used to in the past. I think this is what I think this development will head for.
Yeah, do we have a killer application? I mean, we have so many applications, so we need them all.
Please.
I would say as a comment that a killer application should be augmented intelligence. In other words, if we can add intelligence to ourselves so we can understand the world better, I think will be the killer application.
More questions from the audience? Come on, guys. Don't be shy. Yeah.
This is kind of a comment, wondering question. You decide. One thing that came up in some of the talks today, those mainly related to not just memory replacing memory, but computing in memory, have to do, I think, with introducing imprecise computing through the side door, which is not necessarily bad. In digital, we fell into the trap of all or none, and this may open a channel to it. And it brings also another thought, which is, in some cases, you have a sort of error correction or regeneration that doesn't need to be at the gate level like we do normally in CMOS. It can be later. So the example that Engin gave earlier of the NP complete problems or the simulated annealing, like of bringing it to a reasonable place and then calling upon the conventional digital to take it on from there. So you kind of have the cake and eat it. And I'm wondering whether this may be an interesting opening corridor into new uses, again, not in the strict memory replacement, in the broader things.
So the question, if I understand, is about imprecise computing. Please.
Well, yes, exactly so. And there's obviously, well, I said there's a role for even analog devices and machines, but also for digital. So there's tremendous, I think there'll be a tremendous drive toward providing new devices, new circuits, new chips for the deep learning. So we had Stuart say we need to augment our capability. Well, I'm augmented. What I do is, if I only remember an equation, but I don't remember the equation, I get online and there's some kind of, it figures it out. There's an associative way. So I'm augmented already. If I don't speak Hebrew, I wish I spoke Hebrew, but I'm augmented because I can do translation. If I get to a Hebrew web page, I can do the translation. So that's now being done by deep learning. So it appears in many places. Now, some of them are products, we don't see them, but they're at the data center. And at the data center, we use them, but we don't realize we're using somebody's new product. Okay? And I think we're going to see more and more of that. So yes, I wholeheartedly agree with that comment.
What do you guys think about imprecise memory?
I don't know, but if we look at least data memories today, they are very imprecise. So you do lots of error correction to get the right data out. Even after storing, you have plenty of bits where you have stored something differently than you intended. So if this is what you're talking about, it's...
Can we tolerate computing with memory that is unreliable?
Yeah.
I think even my memory is not so reliable, so probably yes, because one of the things that we need to handle the errors and you know, the tolerant and the update and learn all the time. So we are doing that, and the computer will do that, and the application and memory will do that.
One of the natural boundaries for memory of a computing element is one atom or one molecule. Which of the things that we heard today or not heard is have the ability to approach that?
So I described a tunnel device that was going from quantum dots that were essentially molecular sized and tunneling to another quantum dot. The rationale was not simply to be small, because we will have small devices regardless. The rationale was we needed reproducibility. And with molecules, you can purify them. So chemists have ways of purifying molecules. So the miniaturization argument for molecular electronics failed because we could miniaturize silicon. But the new function of having totally reproducible devices that can be made reproducible by chemical purification, that strikes me as a very strong motivation for going down, not to the atomic level, but to the molecular level.
Professor Aono in Japan, in NIMS, he showed, I think it was 2005, that ionic memory could be an atomic switch. He called it the gap-type atomic switch, where he could put a single atom in and out of contact and get a digital storage from that. And it's certainly something we've been interested in the ionic resistive memory community for some time, creating the right situation within the insulating layer where we could actually switch, in effect, single atoms. And I'm happy to say that the simulation community has caught up with that quite a bit in looking at supercells of atoms, molecular dynamics, and they're pretty convinced that single atom switching is indeed possible. So we're quite excited by the prospects of single atom.
Anybody else? More questions? Yes, Eitan.
I'm sorry to dampen the excitement a little bit, but you guys seem to forget that we still need wires and power supplies and signals. So rethink.
What's the reaction?
So I agree completely that the wires are here to stay and the switch may change. Even silicon might go away and we still will have wires. So I think it's, your point is very, very important. And I've been trying to emphasize the same thing for a period of time, and that is that we'll have a new switch, we'll have various things, but the wires will stay. So if the wires stay, what is the remarkable property of wires? The wires want to work at millivolts. The wires have noise of microvolts, working at millivolts to have good signal-to-noise ratio. We do not have a device that's compatible with the wires. And this is why all of electronics is inefficient by 4 to 6 orders of magnitude. And it's been this way for decades, and we have to recognize that. And the switch has to be made compatible with the wires, and how do we do that?
Anybody has the answer? Please.
Well, but before we rush off that, I mean, there's an obvious assumption that when we talk about single atom devices and single molecule devices, that we're talking about ridiculous densities. But I think, to be honest, it's more interesting to talk about devices that function with attojoules of energy, where you're moving a single atom. To reduce the overall, power requirement. The concept of Internet of Things and this distributed sensors and the likes, where you're literally scavenging energy out of the room, out of the air, out of the ether, I think begs for devices that operate on astonishingly low energies. And I think that's where single atom, single molecule comes in, not trying to wire a gazillion of these things together. Very true.
Let me get back to the issue of the wires. There's one thing that's important, the regularity. In the 70s, there were plans of having big integrated circuits with very regular wires, like IBM Work Computer and all this. Then with CMOS, the thing went away because we all like libraries, and so wiring became something extremely regular and unpredictable. So one of the hope of the future technologies that we can have, again, a regular structure for wiring that can be predictable. What are your comments on that?
Well, so I gave a proposal to Intel once that we could, it was a proposal for how to design lithographic masks. And they said, well, that's very interesting, we'll run a test. And we won't give you any money. Of course, as a university professor, I always want money. He said, no, we won't give you any money, but we'll give you, we'll pay for the mask. And the mask was very expensive. It was about $1 million. And so, and the whole thing was very hush-hush. And I'm still not allowed to tell you the pattern that we did. So we ran the test. They looked at the pattern, and they said, well, I asked them, is this any good? Is this something you're interested in? And they said, yes, it's amazing. You seem to be able to do random wiring. And right now, our plan is to do regular wiring, but you can do random wiring. So I said, wonderful, we'll start a company, and you can be one of our first customers. And we did start a company, but somehow Intel never became a customer. Okay, and then about 5 years later, they made a big announcement that they had adopted that mathematical approach, and they were also able now to do random wiring, very dense. So I think that's what happened, is that we saw examples this afternoon. The lithography today is better than the lithography was before, like maybe 10 or 15 years ago, even though it's much higher resolution. And the reason is we have more sophisticated mathematical algorithms to do the optical proximity correction. It used to be called optical proximity correction, and now I think it's called inverse lithography technology. But I think that's what happened to the regular wiring. It wasn't needed.
I just want to add a few words. Actually, we do regular wirings, even in the existing technologies, and even not scaled ultimately. For example, Intel definitely, for example, what they called now that extreme scaling or ultra scaling, actually it's making a special design of a FinFET transistor where the dummy lines are placed at a certain distance from the operating gate. And the same we do with memories. So to some extent it exists, but it does not actually eliminate the wiring. The wiring remains irregular, but remains.
Okay. You mentioned $1 million, so let's talk about money. I also recall that in the morning talk by Professor De Micheli, there was a point that civilization will need to pay more for more performance. And that was free in the past, but it will not be free in the future. So looking at all these possible new technologies, the emerging memories and other technologies, what are the money implications? What are the cost considerations, please?
Okay. Probably it's a question to me. So my aim is to select the technology that brings money to the company. And it's a very difficult task, actually. And so that's why even for large foundries, and we are now considered a large foundry, about $1.5 billion. So investing into new technologies is a problem. So the CEO will always ask when I will get my money back. And among all these nice ideas that we heard today, to say and to actually to put your head or hand under the axe, it's extremely difficult. So actually what we try to do in order to find something really valuable is to find a customer, an end customer already at the stage when we define the project. If suppose there is a large company, or even not a large company, but a smart company, that wants some kind of a solution. I will give an example. For example, LIDARs or something, or smart radars working at very high frequencies. If suppose there is a startup that said that I'm going to win the market and I will equip all the autonomous car with these radars or LIDARs, so we get into it, and so we invest money to make corresponding development. This is actually the way industry works. Maybe very big guys like IBM or Intel can make a kind of a research focused on something very interesting, but still far from the ground of practical microelectronics. This is how we select the projects. We try to find a customer that backs the project.
Okay.
Yeah. Can I talk more about money?
Please.
Okay, so in the United States now, the old line electronics companies don't really have that much money anymore. And if you look at where the money is, there are some people who have a crazy amount of money. And these are the people who run data centers. So if you're Google, if you're Facebook, if you're Amazon, if you're Microsoft, those four have money for a lot of crazy things. And that's why I brought up deep learning, because if you have some way to accelerate deep learning, they will pay for that. The second thing you already mentioned, self-driving car. They will also they put a lot of money into the self-driving car. So anything, any device that is helpful, that really makes an impact on the self-driving car, like LiDAR and other forms of sensors, that's another thing where there's a crazy amount of money chasing that.
More questions from our audience? Please.
I agree, but I would add also another comment, which is security. Because that's part of the craze about quantum computing now, and there are two major players, Google and Microsoft in this game, is that if you have another paradigm that can break the codes, that actually can change the structure of the economy and the structure also of politics. So the question is probably not really if you can build that, but what happens if your adversary has a computing tool like that, and you're left, you know, with all the great CMOS that doesn't break the codes. So that's another big issue.
So just, I think what you say is very interesting, because, you know, we are a startup company. So would you, I mean, you told us where the money is. So just a question to you, I'm not from the audience, but okay. If you would to develop an application that will be the most potential application for money, what would you develop?
No, don't ask me. All my best ideas have turned out not to have such big markets.
Okay, I think this is a good point to mention tomorrow's panel. Tomorrow's panel is dedicated to business and viability and money and customers and the ability to use the emerging technologies for something useful. So with this in mind, I invite you all to look forward to tomorrow's panel.
Every question will be $100.
Okay, Rafi will moderate the panel tomorrow, and you can negotiate with him. Perhaps he'll give you a better price. Okay, so I think that's the end of the day. Thanks for attending, and the speakers are invited to the evening activity, and see you all tomorrow.
Thank
Good
you.
evening.
Thank you.